The groups SO3, SE2, and Euler angles. What is a group? Monofile discussed this last week. It's a collection of elements. It's closed under an operation. It is associated, has an identity, and an inverse. So the inverse to each element in the group, such if you multiply them together, you get the identity. SO3, we have to start with O3 first. O3 is the group of orthogonal 3x3 matrices. Orthogonal is you take an element in the group, multiply it by the transpose, and you receive the identity. These matrices act on vectors, and these vectors are in R3. This group has a property that lengths are preserved, and you can see this mathematically here. So take some length, and then we're utilizing the orthogonality property in order to get back to the same length. Does that make sense? Okay, so something that's interesting because of this length preservation is in quantum mechanics, we take probabilities that some state psi will go to some state phi. And this probability is a length. And we have that if we operate some orthogonal matrix on this, on both states, then we have that the probability, because again of the properties of orthogonality, the probability is unchanged. So probabilities are conserved in these groups. Another property of O3 is that I'm letting R be in O3. So R, so the determinant of all elements in O3 is equal to either plus or minus 1. And if you'd like to see a quick proof of that, we have that RTR is equal to the identity, and the determinant of the identity is equal to 1. So then the determinant of RTR is equal to the determinant of R times the determinant of RT, something we know from linear algebra, and this is equal to the determinant of R squared. Again, because linear algebra, because we know that's equal to 1, we can take the square root of each side and get the determinant of R is equal to either plus or minus 1. And so all of the elements in O3 either have a determinant equal to plus 1 or a determinant equal to minus 1. And we can consider these two sub-collections. We can split them up into those with a determinant equal to 1 and those with a determinant equal to minus 1. The determinant of the identity is 1. So this sub-collection does not contain the identity. So if it doesn't contain the identity, it's not a subgroup. So we don't consider that case. We consider this case. And then we call this property of the determinant equaling plus 1, we call this property special. So this leads us to call this new subgroup SO3. And SO3 has all of the properties of it also. The SON structure, there are other, this means 3x3 matrices, there are other dimensions of matrices. So this SON structure depends on n times n minus 1 over 2 parameters. So SO3 depends on 3 2's cancel 3 parameters. These 3 parameters we call theta 1, theta 2, and theta 3. These parameters are defined on negative pi to pi. And SO3 depends on these parameters continuously, so it's a Lie group. This Lie group is also a manifold, and it's a manifold of radius pi. And we have that on this manifold, antipodal points are identified as the same point, and you can physically realize that by rotating something by pi, and then rotating it by negative pi, you end up with the same result. So we have the integral point to the safe point. So if we take a path from the identity out to some point pi, we get to the point negative pi, because they're the same point. And then we make our way back from negative pi. This closed path can't be shrunken down to a point. So heuristically speaking, this group is not simply connected. So SO3 is not simply connected. And because it's not simply connected, there exists some group in which SO3 is a subset of that group. That's a subgroup of that group. And the larger group is simply connected. And that larger group is called the universal covering group. And so the universal covering group of SO3 is SU2. That's their relation. And this universal covering group has a property such that the projective representations of SO3 are equivalent to the regular representations of SU2. What is that and why is it important? So projective representations. What are they? Why are they important? So in quantum mechanics, we can take expectation values of things. So we take an expectation value of, say, momentum on a state psi. Then we notice that if we're taking the expectation value of momentum on a state psi, then we result in the same thing if we wanted to do this on the state e to the I theta psi. Because we see that psi e to the minus I theta p e to the I theta psi. And these e to the I thetas are just numbers, so they commute, and so they can subtract their exponents and go to 1. So we have the same expectation value. So this is showing that all of these e to the I theta psi's are getting mapped to a single psi. And this is a projective space. So we have to use a projective representation. And the primary definition for the projective representation is if we take some representation U of R1, some U representation of R1 times U of R2, then it needs to be closed, and it is, but we get this phase factor of U R1 R2. And the difficult part about this is this phase factor. Theta is dependent on R1 and R2. And we don't know how to find that theta. It's difficult to find that theta. So, yeah.
Okay.
Yeah.
Or shall we ask at the end?
You can ask now if you have it.
What's R1 and R2 again?
R1 and R2 are just some elements in SO3.
Oh, okay.
So R is some element in SO3. And later I'll use B for SU2, sorry. Just some arbitrary element.
Okay, and what's the notation? U of R1?
A representation of the group element.
Uh-huh. Okay.
Where representation is you just take some element in SO3 and make a representation, and that representation makes it into some n by n matrix.
Okay.
And this is showing that this property is closed, but we get some phase factor. And this phase factor is what's difficult in quantum mechanics. And this is called the projective representation. And instead of using these projective representations in SO3, we instead use the regular representations of SU2. Because we don't have these phase factors to deal with. That was the interesting side note. Which brings us to SU2. Further question? No? Okay, SU2 is the group of special unitary of all of them, special unitary 2x2 matrices. Where special we defined before, determinant is equal to 1. Unitary, similar to orthogonal, unitary is some B in SU2 times a transpose conjugate is equal to the identity. This one's also length preserving. It can be seen with the same proof as before because of this fact. Interesting. So SU2, the SUN structure, depends on n squared minus 1 parameters. And so SU2 depends on 3 parameters. SU2 is the symmetry group for the weak force. So these 3 parameters correspond to the W plus, W minus, and ZK bosons. And then SU3 corresponds to the strong force, and U1 corresponds to the electromagnetic force. The Lie algebra, a Lie algebra is a tangent plane at the identity of a manifold. And SU2 and SO3 are isomorphic at the identity. And this causes their Lie algebras to have the same commutation relation. So we have generators which satisfy the same commutation relation. And we're going to take infinitesimal transformations about the identity, and then we're going to exponentiate them to result in elements of the group, just like Timothy did last week. I'll do it a little bit quicker because he did it last week. So we have that. Their lead algebras are isomorphic, so we have, for the generators, they both satisfy that Ji, Jj is equal to I, epsilon, Ij, K, times some Jk. So they both follow this commutation relation. And to make an infinitesimal rotation about the identity, we start at the identity and we go some epsilon far away from it, times some J. And then we do this in steps, and we do it n times. And then we take the limit as n goes to infinity, and we notice that this is the definition for the exponential. Now it's theta instead of epsilon because we've gone some finite distance with doing the limit.
On which does this theta depend?
On what does theta depend? Theta is...
Epsilon, probably.
Epsilon doesn't depend on anything, it's just a little bit.
Yes, but theta depends on epsilon, doesn't it?
Theta is epsilon, but a larger quantity.
So it depends on it.
Yeah. We can express any element in SU2 in the following form. I alpha J1, maybe I beta J, J3, J2, maybe I gamma J3. We can explicitly write it in this form for any B in SU2, where these alpha, beta, and gamma are the Euler angles. And now I'll draw the Euler angles. I think I have enough data. we have some sphere with some axis in it, x, y, and z. This is some plane, and this is some plane. So x, y, and z. We're going to rotate about the z-axis a little bit. So the z-axis is going to remain the same. But our x and y are going to rotate. Our x and y are going to rotate a little bit. So x and y, x prime and y prime. So now we have c prime, x prime, y prime. Now we're going to rotate about y. Now we're going to rotate about y prime, pardon. So we just rotated x, y, and z. We just rotated. And now we're going to rotate about y. So now x and z are going to move. And we notice that they both lay on this plane, so they're going to follow that plane when they rotate. So we're going to rotate about y prime, such that z is going to rotate down a little bit, z double prime, and x is going to go down a little bit, x double prime. And I should also tell you that x to x prime, this first one, we call that gamma, y to y prime we call gamma, and then prime to double prime we call beta, prime to double prime we call beta. And the last one's going to be about z double prime again. So now our x prime and our y prime are going to rotate. And for that we need another line. And so this x double prime and this y double prime will rotate up this while the z double prime stays the same. I'm only going to rotate a little bit so we don't get too confused here. Hopefully we're not already very confused. Are we very confused?
All the time.
Okay. So those are the Euler angles. And we can express any element in SU2 utilizing these Euler angles as this. Now, the last question that I'm going to pose to you is how do we know that this is still an element of SU2? It needs to be closed. Well, first I'd like to point out that this does not equal e to the I alpha J3 plus beta J2 plus gamma J3. And that's because addition is commutative, but these guys are not commutative, as we saw here, to the commutation relation. So if we were to make this true, then we would lose this information, so this is not true. So how we do this instead is using the Baker-Campbell-Hausdorff theorem. And so we have that e to the h J1 J2, where h J1 J2 is equal to J1 plus J2 plus 1/2 commutation relation J1 J2 plus 1/12 commutation relation of J1 with the commutator of J1 J2. And it goes on like that. It's an infinite sum of nested commutation relations. And we have that this, so if we were to take this, then we can see that we can split these e's up. So we can have e to the this times e to the that, etc. And we know that this is in the Lie algebra. So then the exponentials of all of these this is in the Lie group still. And that concludes, and are there any questions?
I have a question. Why don't you rotate just once to the z-axis? The z-axis? No. You can, for example, okay. No, I see.
Yeah, this is a clever way to be able to show any rotation.
Yeah. Okay, cool.
And then You guys have a week apparently to think of questions because I don't think Gleb is coming today. All right, thanks.
So these are the Euler angles for SU2 or for SO2.
Good question. It's for SU2, but what we can do with the representations of the generators is we can take the representations of the generators of SU2 and represent them as generators of SO3.
Okay. You have to keep in mind that we didn't introduce generators and representations yet.
Okay.
So maybe it would be good if you explain them shortly.
Yeah, sure. I'll do that now because it's interesting and important. So representations, I said earlier, is just you take some group element, you represent it, and you end up with some n-by-n matrix. And with that, you can act on vectors. So the first example I'll show you is a representation of things about the x, y, or z axis, because that's something that we can physically realize. So some R1, where R is in SO3. This R1, 1, 0, 0, 0, cosine theta, negative sine theta, 0, sine theta, cosine theta. So this is some rotation about the x-axis. So this is what an element looks like. It rotates something. Similarly, we can look at the x, y, or z. And then the generators are one, and these are the generators. And this is just a convenient choice of generators. We can do another 3 linearly independent set of matrices. Go for it.
How are generators defined? What is a generator?
A generator is defined as Jk equals I Rk of theta, the derivative with respect to theta, at theta equals 0, where k, in this case, runs from 1, 2, and 3.
For any Lie algebra of dimension 3 with some conveniently chosen element.
R, yeah.
Okay. The interesting point is how you choose these elements. Is it?
We can actually find them. So if we notice these look similar to the Pauli matrices, we can find these elements. And I have done that. I unfortunately don't know where, but it's very interesting. Where have I done that? In here. And I'll just show that to you because this is really long and convoluted. So finding basis vectors for the algebra of SU2. And so we know this, and what we're about to do is prove it. And so the first place we see it, so this is all the information to get there. So the first thing that we notice is this is what we end up with. Okay, and so we go through the commutators. We're looking for a commutator that commutes. And so we use t squared and the z. And then since they commute, they share eigenvectors. And then we label the eigenvectors L and M. And we have this relation, which we might know from quantum mechanics. They come, I don't remember where they come from, but they have some reasoning. And then so each irreducible representation of SU2 is labeled by which integer or half integer it's in. So you can either have one-dimensional scalars, 2 dimensions of vector, depending on what L you're using, L0, 1/2, or L1. And then it can be find by finding the matrix elements. So you find this irreducible representation by finding the matrix elements of each of these. And so this example is follows. So we pick L equals 1/2 and N equals either -1/2 or +1/2. So we act on 2-dimensional vectors, and we want L equals 1/2 representation. So we need 2 by 2 matrices. So these matrix elements for this specific setup is, and then we just act in here, this 1/2 M because of this LM, 1/2 M TC, 1/2 M, and then we do some computation of these inside elements, but all the eigenvectors are orthogonal, so we end up with the delta function. And then with this delta function, we put in different combinations of the 1/2 and -1/2 of the L and M, where the matrix is set up as M here and M prime here. So then when you put M prime into this delta matrix, 1/2 and 1/2, and you end up with 1 in here, and then you do that for all 4 spaces.
These are elements of the Lie algebra.
Yes, they're generators of the Lie algebra.
Okay, so you find the generators by as orthonormal as a basis of the Lie algebra. Okay. And then you construct the RKs. Because looks like your definition first finds the RKs and then constructs.
I think you can go either way. Because this is saying that you have some RK and then you're finding the generator, whereas in this case we were finding the generator. So it looks like just different approaches to the same problem.